All right. Today, we'll see how this goes because I'm kind of winging these as I go. Last stream was supposed to be a bit of an overview of how the whole thing works and what everything on here is. Today, I want to start getting into some of the details of using it. Not going to get too deep, but I think maybe I'll show a little bit more about the limited peripherals that are on here, and then maybe inputting instructions for the first time. So we'll go through, I want to show a little more information on this output register because I kind of glossed over it last time, and we can look at that this time, which you don't need to run the CPU to play with that and understand what it does. And then I think we'll maybe try putting in a basic loop to the CPU, but we'll see how far we get because I will probably want to go over hex and binary and how all that works as part of this as well. So let's start with this because that'll help me give an introduction to how addressing works. For starters, let me plug this thing in. So last time, I went vaguely over the address and data lines without really mentioning anything about how they represent numbers or what have you. For people who are already quite familiar with binary and hex or what have you, don't let this, you'll just suffer through. But of course, these switches represent a number in binary. That's the whole thing. And we're going to need to know that and a little bit of how that works in order to understand how we can write to this thing. Because right now all we've shown is writing to and reading from RAM. And as it turns out, RAM is not the only thing that our CPU or our control section can talk to, because of course you need some kind of I/O so that you can communicate with the world, which is what that is. That's our only I/O on this whole thing. So how does that work? So this is mapped. Let me see if I have my... Yes, I do have my monitor set up. Let me go over to the GitHub page. Okay, so at the bottom of this page, you'll find a lot of stuff on this page, but there's a section called Memory Map. Every computer has some kind of memory map, which just means where things are located in memory space. So firstly, as I mentioned last time, this is a computer with a 8-bit bus and a 16-bit address space. Getting more into how binary / hexadecimal numbers work in the future, all I'll say right now is that you can represent about 65,000 addresses of locations holding 8-bit data using 16 wires. And basically what we have is, this will make more sense in a second when I start going into hex, but since it's 65K of total space, the way it's divvied up is that it's not all RAM. The lowest area from the very first address at 0 through up to, ignore this number for the moment, but up to about 32,000 positions after that are RAM. And then from the very top of memory, about that 65,000th position down to 32,000 locations below that is also RAM. So you've kind of got this sandwich of 32K of RAM in the very lowest area and 32K of RAM in the very highest area. And then the middle, which is its own... Actually, this is incorrect. Sorry, 16K. This should be 16K because it's 16, 16, and 32 for a total of 64, 65. But right in the middle, anything in this area is where our I/O stuff is mapped. So a quick gloss over of how I/O is connected to a computer in the first place. There's a ton of different ways, but generally they fall into two camps, which is memory mapped I/O, and I don't know if there's really a better word for it, but like direct I/O. So, for example, in an x86 processor, an Intel processor, which this is not, there is actually a special set of instructions that there's an input instruction and an output instruction, and those cause there's a special set of wires on the CPU that tell only the chips that are listening to the bus as I/O devices in the I/O space, which is totally separate from the memory space, to listen or to write data or whatnot. That's a touch complicated, and we're not going to go into it because we don't have an Intel processor here. So what this is using, since this CPU has no idea about any of that stuff, all it has is it can either read to memory or write to memory, and that's it. You know, it has 16 bits of address, 8 bits of data, and a couple control lines. That does everything. So what you have here is memory mapped I/O, which is exactly what it sounds like. Basically, there are devices that show up in memory, and you interact with them exactly like they were memory, so you just store a byte there or read a byte from it. But instead of just being generic RAM, it's some piece of hardware that does something. In this case, ours is very simple. Like I said, you can kind of think of the chip that's here as more or less hotkeys. There we go. As more or less just one position of RAM. They can hold an 8-bit value. And what that memory map is saying is that anytime you write to anywhere in that middle 32K of memory, anywhere above the first 16K and below the last 16K, it will write to this chip. No matter where you write, anywhere in there, it writes to this chip, because that's just the way it's wired up. More or less, to go into a little detail, the RAM chip has a bunch of address lines wired up to it because it needs to be able to distinguish between, 32K, because we have two 16K chunks of memory. But this has literally one wire going to it that just toggles on if you want it to capture whatever value is coming from the bus and transfer it over here, and that line turns on anywhere in that middle 32K. So I will demonstrate and at the same time teach a little bit of how binary and hex work. So I won't even bring up binary or hex at the very start again. I want to go very simple. I will show you how to write to this register, and then we'll kind of work backwards to understand how that matches with that memory map that I was showing, and eventually we'll get back to how those numbers actually correspond to, well, how those hex numbers actually mean anything and relate to what I'm about to do with these switches. So right now, let's set this to all 0. I am not in run mode. What I'm going to do is I'm just going to set the highest address pin on. And I am going to, here, let's just turn on the lowest data bit. I am going to hit store. And as you can see, it went over here. Okay, and kind of per what I was saying, if I set any of these, do the same thing. Let's change the data value. So now we have some crazy thing that this is still high, but some of these are all over the place. Some of them are high, some of them are low. But it will still transfer what I had on the switches over here into there. And if we just keep experimenting, let's try flipping this switch. And same kind of garbage. And let's set up some new different data value. Okay, so that transferred that over there as well. This switch is off, this switch is on. All garbage. Let me try turning these both on. Nothing. If I turn them both off, nothing. So the rule is there's some glue logic in here, but really all it's saying is if this top switch is on, it doesn't care about any of these lower switches. If this top switch is on, let's just put that, change some data so that we can see it change. If this top switch is on, or if the second top switch is on, some other garbage. but not if they are both off. And not if they are both on. Random data. And that's it. That's the entire rule for under what conditions this gets written to. Now, this is nothing specific about computers in general. This is something that's very specific to how this board is wired up, just to be clear. But that's how the hardware works. Just if this switch is on, it will write there. If this switch is on, it will write there. But if they're both the same, it will not write there. That corresponds directly to, let me go over to, now we will give the quick introduction on hex and binary, and I'll gloss over, you can look at this more on your own, but let me get a notepad here. Of course, I am not well prepared for this. Let me make sure the font is nice and big. Okay, that should work. Let us represent those address switches with ones and zeros, because that part's pretty obvious, right? The correlation between binary and these switches. So, let's see, 4, 8, 12, 16. So these are lined up just like our switches. This would be all of our switches off. This would be that top switch on. This would be the other switch on. This is them both on. You get the idea. So, like I said, just gonna gloss over this because there's a lot more resources that you can learn about how to read hex and binary, and I don't know who already knows this stuff. But with binary, it's, here's the most straightforward way to think of binary versus decimal. So it's the same thing, you know, they're both just numbering systems. And a numbering system in decimal is you have positions, and each position can hold 1 of 10 characters, right? 0 through 9. And then in decimal, in fact, let's count decimal. So you go 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you move over a place. And what this represents is that you have 1 10, right? This is your elementary school stuff. That's 2 10s, that's 3 10s. So this boils down to, if you want to look at it in a more mathy way, like 30 is 3 times 10 plus 0 times, where's my asterisk? Times 1. And like 31 is 3 times 10 plus 1 times 1. So on and so forth. And that's how a number system works. Every time you move over 1, you go up by a power of 10. And binary is the same thing, except you only have, let's not even think about the powers. I'm just going to think of it in the most simple terms of counting. So again, when we were counting, we were going 1, 2, 3, 4, 5, 6, 7, 8, 9, and when we ran out of characters that we could use, we rolled over and incremented the next place, right? Just like an odometer. So it's the same thing with binary. This is 0. If we want to count up, we increase our lowest value, and now it's 1. This whole number is 1. And then if we want to increase it again, in binary, we've run out of symbols to use. So we wrap, and we increment the next location. So this looks like a 10, but that's just because you're used to decimal. What this represents is 2. Because 0, 1, and then we roll over 2. That's the second value we can represent in the binary number system. And then it just continues, you know, it's the 1, 2, we increment 3, and then we go to increment again. We have to roll over and increment the next place, roll over, increment the next place. 4, and then so on and so forth. 5, 6, 7, 8. So you just keep incrementing and rolling over. But one interesting thing that you will note that is pretty useful is that that's 1, right? And we went through, and that was 2, and then we had, if we set this was 3, and then the next value was 4, and that was 8. So, of course, they're powers of 2, which gets back to the powers thing, but that means you can pretty easily think, if you can remember the place values of each of these, which is 1, 2, 4, and 8, you can learn hex-ish. So that's how binary relates to numbers. It's just a different way of counting. And hex is the same thing, but the reason we use hex is because it corresponds really well to binary. So there's a reason I have split these up into groups of 4. It's because you can represent up to 16 values with a group of 4 bits, which is pretty easy to see. So if we were at 8 here, that's 9, 10, 11, 12, 13, 14, 15. And of course, that is our 16th value because 0 is the first value. Just like we have characters 0 through 9, and that's 10 characters. So the nice thing is, in hexadecimal, each character can have a value between 0 and 15. So hexadecimal is kind of just a nicer way of writing binary. In the same exact way, you can correlate it back to decimal, or the counting that you're used to, in that same kind of counting method. So ignoring the binary for a second, let's count in hex. So it starts with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But we can go up to 15. But we've run out of characters. So we can just start using arbitrary characters to represent numbers without rolling over to the next place. Because all they are is just arbitrary symbols at the end of the day. You could use a pile of sticks to count. Like, it doesn't matter. They're just arbitrary. Like, the symbol 9 doesn't mean anything. So let's just say that we start into the alphabet after that point. So A is going to be the 10th character in hexadecimal. B is the 11th, C is the 12th, D is the 13th, E is the 14th, and F is the 15th. And again, the whole thing is hexadecimal, like I was saying, we wanted 16 value, or 16 potential values or characters in each place. So ending at F is fine for our purposes. And then same thing, if you go past the end of that, then we're going to say we only use the characters up through F, and we wrap an increment. But now, instead of being 10, but also instead of being 2, since we're working in hexadecimal, this is 16, right? Because to count again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And it can be a little bit mind-numbing because we also, in the English language at least, and most languages, we also use a base 10 system for describing our words. So, like 16 sounds like, 2 numbers, but this represents 16 things as much as the number 16 does. You just have to know what base you're working in. So then, now let's correlate that back to binary, and I will get out of here and we'll get back to actually using the dang thing. So, how does hex potentially correlate to binary? Well, if each of these groups of 4 can represent up to 15 possible values, and each character in hexadecimal can represent up to 15 possible values, then they just correlate 1 to 1. So, for example, let's say the bottom one is our hex digit, the top one is our binary digit, and they're the same thing. We're just going to count in both hex and binary at the same time. So that's binary 1, that's hex 1. That's binary 2, that's hex 2. binary 3, hex 3. Oop. Binary 4, that's hex 4. Binary 5, that's hex 5. Binary 6, that's hex 6. Binary 7, that's hex 7. Binary 8, and hex 8. Binary 9, and hex 9. Binary 10, and hex 10. Binary 11, and hex 11. Binary 12, and hex 12. Binary 13, and hex 13. Binary 14, and hex 14. Binary 15, and hex 15. And then if we do the count and wrap thing, these are all going to wrap. We have to count the next one. That goes to 1. Hex 1. This goes back to 0. And so this is binary 16, and this is hex 16, which you'll remember from our counting earlier. That's true. This is 16, and we just counted through this, so we know this is binary 16, and they correlate. So it's cool because you can, because of that, the way the numbers divide out, basically, you can use one hex digit to represent every grouping of 4 bits. And the extra nice thing is that a byte, which is what we usually work with, it's kind of our common unit in computing, is 8 bits, right? So that's just 2 groupings of 4. So you can represent any 8-bit number cleanly with 2 hex digits. And again, it's just a tool. You can convert between decimal and hex and binary, and there's nothing really special about any of them. It's just, it all correlates back to, we can set this on switches and store it in, memory cells that can either store having voltage or not having voltage, and we can relate that all back to numbers, which makes it very useful because then you can do calculations with them. So what that then finally boils down to at the end of the day is, let's go back to talking about those top 2 switches and how they cause that output register to be accessed or not. So if this is on, let's just write this in hex, because writing stuff in binary is really, really annoying and basically unreadable, which is the whole reason that people use hex in the first place. You'll also see octal around, which is base 8, and you can represent up 8 numbers with 3 binary digits, so it's the same idea, except you're representing 3 digits at a time, and your digits are 0 through 7. But nobody really uses octal much for anything anymore. They usually use hex because it fits into a byte nicely, and if you tried to use octal, you'd have 3 bytes and 3 bytes, and then 2 little orphan bytes, and nobody wants that. So anyway, so this is 8,000, right? Because as we said before, this is binary. Well, this correlates to hexadecimal 8, which is what that is, and these are all 0. So this is hex 8,000, which correlates to some decimal number that I have no idea what it is. I could guess. I could do the math on it based on the way that I set things up. That's got to be. Actually, I guess our first address for that switch would be when the low one is on, right? Because this is a lower valued place than this, and it was if either of them are on. So this is 4,000. So yeah, so this would be equivalent to like 16,000 something, but I have no idea because it kind of doesn't really matter because you don't ever, unless you have a need for representing this as a decimal value, there's no real need to know exactly what decimal value it is. And that'll make more sense as you do this kind of stuff, but like thinking of it, that it's really important to know what the value of this is, it's kind of not to work with things. It's not really that important. But anyway, so this switch being on is equivalent to hex 4,000, and this switch being on is equivalent to hex 4,000. And like I said, the rule for the circuitry was if this switch is on or this switch is on, then we are selecting that that output register. So that means our lowest number was that 4,000 that corresponds to accessing that area. And then if we, the biggest number we can represent here is, we can't have that one on because it was either or, but we can have that one on, which is the highest placed digit in this whole thing, so it's the biggest value. And then we said we don't care about any of the rest of these, so we can replace these all with ones, right? And if we convert that to hex, then that becomes, let's see, so this is 8 plus 2 plus 1, so that's 8, 9, 10, 11, so that was hex 10, 11. That's 15, which is just our last digit, F, F, F. So what we've derived here is that the lowest address that corresponds to that turning on that chip is that 4,000 hex, and the highest is BFFF. And if we go back and look at that memory map, you'll see from 4,000 to BFFF is read data switches, write user register. So we've gone soup to nuts from switches to that's what these values mean. Sorry if this is fuzzy. Let's see, I can zhuzh this up for you. So that was the the very non-deep dive into hex and how it relates to this machine. Now the nice thing is, again, you don't have to remember many addresses because you just have a chunk of RAM here, and then this whole thing correlates to writing to that register, and then you have a chunk of RAM here. So there's not really much to keep track of in the memory map because there's only one peripheral. There actually is, I'll just note, but we're not going to really go into it yet today. You'll see this says write user register, which user register just means that chip and the LEDs that are strapped to it, and read data switches, but I didn't go over reading anything. So if you write there, it will, you know, put those values, basically store them in these LEDs and you'll see them. Reading data switches is what happens when you read from that same location, and it basically lets you read the value of these switches when the thing is running, but I'm not going to get into that yet because they're a little funkier. But that's it. That's all the I/O on this thing. So I'm going to go back to putting things into that register for fun. Right, so let's clear it out. There we go. It's empty. And that's, we now know, it's not just that switch on, it's 8,000. Wow, I've been recording for a little while now. So I think I will end this one there because I keep saying 10 to 15 and then it ends up being like 30 minutes. And this will probably be like 20 minutes when I chop it down. And I think that's a lot of information right now. But those are the two things for today. It's a little primer on how these correlate to actual numbers and how you can use this thing. The last thing I will say is, of course, so we're not in run mode right now. We're like, I could read or write to RAM here too. Like so they're both off, which means right now this is address 0, which was RAM. And so I can, as we were doing before, now I'm viewing RAM like we were doing the other day. So if I'm not in that area, if I don't have one of these two switches but not both on, it'll go over there. Otherwise, it's all RAM, and the same thing that I was saying the other day. But that also means now we understand a little bit more. This is address 0. This is address 1. This is address 2. Address 3. Address 4, so on and so forth. Address 5, address 6, address 7, address 8, address 9, and the only reason I'm counting this high is this is address 000A, or 10 in decimal. And that's how you can get those switches to correspond to numbers. So next time around, I will actually we'll put some instructions in this thing. I promise you, we'll get there. But in programming mode, again, these address switches just put values on the address wires,
and these data switches just put values on the data wires when you press this button, or they show whatever is putting data onto that bus when you're not pressing this button. But when you switch over to run mode, the CPU is just doing the same thing, but automatically. So you can also write programs, and we'll do this later, to if you have instructions in RAM that the CPU executes that tell it to store information at, say, address 8000 hex, it'll put those in that register. So it's not just for us playing around over here, it's that you can use that from an actual program that you're running on the CPU too when we get there. And that's how we'll be able to see output from the CPU. But that is all for today. Next time, we'll actually run a program.